Hello, everyone, and welcome to Lecture 8 of Computer Architecture. Today, we're going to talk about building an ALU. We started talking about building an ALU last time. We're going to continue talking about it and hopefully finish today. So a quick review of what we covered last time. We started talking about building an ALU. We said that an ALU was a logic block that takes two operands and gives the result, and the operation that it performs on these operands is determined by another signal, which is some operation. So an ALU could maybe do a bitwise AND, bitwise OR, addition, subtraction, comparison, things like that. And here, A and B could be kind of any number of bits wide, and the result would be the same number of bits wide. We said that different architectures support different primitive types with different widths. So, for example, MIPS supports 32-bit and 64-bit. Some architectures may support 16 bits. So we'd need an ALU that supports operands with that number of bits. So we said that we're going to assume that we can construct an n-bit ALU by connecting n 1-bit ALUs together. And we set off to design a 1-bit ALU and then showed how to connect them to get n-bit ALUs. So we started with logic operations, and we said that we can build a 1-bit ALU that does AND and OR by simply passing the operands to an AND gate and OR gate, and then using the operation signal to select one of these two results. Then we moved on to, and we said that we can put these 1-bit ALUs together to form an n-bit ALU. So here, each 1-bit ALU does one of the bits in the n-bit input, or processes one of the bits in the n-bit inputs to produce an n-bit output. We then looked at addition, and we saw how addition, the result of an addition does not only depend on the input bits A and B, but there's also this notion of a carry in and a carry out. So the 1-bit ALU for addition needed to have a carry in and carry out to the 1-bit adder. And what we did is we connected these 1-bit ALUs with adders inside of them together, where the carry out of one of the 1-bit ALUs goes as the carry in to the next 1-bit ALU. And because here we have this carry bit rippling across the ALU, or the adder that's kind of inside of this ALU is called a ripple carry adder. And there are other kinds of adders that are more efficient than a ripple carry adder that are used in practice. But here, for simplicity, we're kind of showing you the ripple carry adder because it's the simplest to understand. Next, we looked at subtraction. We said that subtraction can be expressed as adding the 2's complement, and the 2's complement can be obtained by inverting a value and then adding 1. So we implemented subtraction in ALU by taking advantage of the fact that we already have addition, and we inverted the second operand and added 1. And the way we supported that is by having a multiplexer that selects between B and not B, where B is the second operand. So if we're doing subtraction, we're going to select not B. If we're doing addition, we're going to select B. And then we also would pass in 1 for Cin to get the +1. So we got not B, and then we're going to get the +1 from Cin 0. So by doing that, so if we have subtraction, B invert is going to be 1, Cin 0 is going to be 1. Otherwise, if we have addition, B invert is going to be 0, and Cin is going to be 0. Next, we looked at building NOR and NAND operations, and we said that we already have an AND gate and an OR gate. And by De Morgan's law, the NOR operation is like having, so not and or B is like having not A or not B. So what we did is we used the AND gate that we already had and simply inverted the inputs to the AND gate in order for us to get a NOR gate. We already had B invert from subtraction, so the only thing we had to add is also be able to invert A. And similarly for NAND, we inverted the inputs of the OR gate, and that gave us a NAND gate. And then finally, we looked at set on less than. And for set on less than, we observed that we can find that A is less than B if A minus B is less than 0. And we know that A minus B is less than 0 if the most significant bit of A minus B is equal to 1. So this is a property of 2's complement. In 2's complement numbers, if the leftmost bit is 0, then that's a positive number. If the leftmost bit is 1, then that's a negative number. So we said that ultimately what we want the result to be 0. In other words, we want all the output bits to be 0. If the subtraction is positive, in other words, the most significant bit of a minus b is 0, and we want the output to be 1. So all the bits are 0, but then the least significant bit is going to be 1 if the most significant bit of the subtraction is 1. So in other words, our least significant bit is going to be equal to the most significant bit of the result of the subtraction, and all the other bits are going to be 0. And the way we implemented that is we had a fourth input to the multiplexer, which we called less, and in the n-bit adder, and we also had modified the 1-bit ALU for the MSB to sneak out the result of the subtraction. And then finally, in the n-bit adder, we set all the bits to 0 for less, except for the very first 1-bit ALU. For the less for the least significant bit, ALU is going to be equal to the result of the subtraction in the most significant bit. And this is how we implemented set on less than. So that's what we covered last time. Does anybody have any questions before we move on to today? I see there's a question in the chat. So someone's asking, we said 0 is low voltage. So if we don't have any voltage, does that mean we're choosing a 0 operation? So in this course, I don't want you to be too concerned about how the circuits are working at a lower level than logic gates. Okay, so don't worry about, transistors and how they're being used. There's entire courses on that at AUB, so you can take those courses if you're really interested. But in this course, you shouldn't be too concerned about that. But the short answer is no. Having an open circuit is not the same as having a 0 voltage. You said you don't have any voltage. So by don't have any voltage, I assume you mean that you have an open circuit. There's another question. Someone's asking, where do we connect the set that we're sneaking out of the 1-bit ALU? So let me go back. So here we said that this set over here, this is the result, the most significant bit of the result of the subtraction. So the result of the subtraction comes out here after the adder. Okay, and this 1-bit ALU here is for the most significant bit. So this set operation is going to be the most significant bit of the result of the subtraction. So what we did is we took it out from here. So this is the most significant bit, the 1-bit ALU for the most significant bit. We took set out from here and we turned it all the way around and brought it into the 1-bit ALU so that over here it comes in as less and it comes out as the result. Okay. So the answer is that we take set from the bit 1-bit ALU for the most significant bit, and we bring it in as an input to the least significant bit, and that's going to be our result. Okay. Any other questions? Okay, if there are no other questions, then let's get started with today's material. So today we're going to continue talking about building an ALU. So one more operation we want to look at is equality. So we've seen how to do AND and OR, NAND and NOR. We've seen how to add, we've seen how to subtract, and we've seen how to compare if something is less than something. What's left is to be able to compare if something is equal to something. So the equality operation, the way we're going to use it eventually when we come to build a processor is that we're going to set some flag to 1 if A equals B, and otherwise we're going to set it to 0. So usually we use equality as part of some branch instruction where we want to maybe take, go to this part of the code if something is 1, if something is equal to something, or go to this other part of the code if something is not equal to something. So what we're going to do is we're going to set a flag if A is equal to B, we'll set it to 1. Otherwise, we'll set that flag to 0. Okay, and again, like I said, this is usually used by branch instructions, instructions that jump to different places in the code. And those are usually come out of if statements and for loops and things like that. We can implement equality again using subtraction. So just like we did comparison less than using subtraction, we can implement equality as well using subtraction, because we know that if A equals B, then A minus B is equal to 0. So if and I already implemented subtraction in my ALU, so for me to be able to support equality comparison, all I need to do is use the subtraction that I already have, right? And check if the result of the subtraction is 0. Now, how do I know if the result of the subtraction is 0? How do I know that an n-bit number is 0? Well, quite simply, a number is 0 if every bit is 0, exactly. So the result is 0 if all its bits are 0. So then how do I support equality in my ALU? Well, simply, I'm going to do a subtraction, and then I'm going to check if all my results are 0. So here I actually don't need to modify my 1-bit ALUs. My 1-bit ALUs stay as they are, and the operation that I'm going to pass is just subtraction. But what I'm going to do is I'm going to take the result of my subtraction, and I want to check if all their bits are 0. So I'm going to take result 0, result 1, result 2, result up to result n minus 1. And I want to check if they are all 0. Now, what logic gate gives me 1 if all the inputs are 0? Who remembers? NOR, exactly. So NOR gives me 1 if all my logic gates are 0. So I'm going to pass all the inputs to a NOR gate, and then the output of the NOR gate is going to be a 1-bit flag that will tell me if my result is 0 or not 0. Okay. Why NOR? Because if all the bits are 0, so if you think of the OR gate, if any of the bits are 1, the output of the OR gate is going to be 1, so the NOR gate will be 0. So here, this flag that tells me if something is 0 will be 0. In other words, it's not 0. And then otherwise, if all of these are 0, the output of the OR gate will be 0. So the NOR gate will give me 1. What that means is that the 1 is telling me that it is true that this number that we just got as a result of the subtraction is 0. Okay, so this is how we implement equality. Any questions about equality? Should be fairly simple. Okay, well, next we're going to look at overflow. So let's look at overflow. So we said that, if we have an n-bit ALU, there's only a finite set of numbers that it can represent, right? If it's unsigned, then we can represent to the power n minus 1 numbers, so from 0 to the power n minus 1. If it's signed, that means we can go from negative to the power n minus 2 to the power n minus 2 minus 1. So we have a finite set of numbers that can be represented. So if I take numbers and add them together such that, or subtract them such that the result is going to be larger than what I can represent with my n bits, that means I have overflow. And I need to be able to detect overflow, because if I have overflow, this means that, my ALU failed to give me a correct reason. The program is doing something wrong. They're trying to add, two numbers that are too large, where their sum is too large to represent. So I need to be able to warn, to kind of give a warning that there was overflow that was detected. So how do we detect overflow? Well, quite simply, the cases where I have overflow, here we can look at A and B, which are my inputs, and the sum, which is my output. Now, if I add two positive numbers and get a positive number, then that means I don't have overflow. This looks reasonable. But if I add two positive numbers and get a negative number, is that possible? Is it possible to add two positive numbers and get a negative number? It's not possible in kind of real math. It's not possible. But if in my ALU, if I add two positive numbers and the two positive numbers are too large to represent, what's going to happen is the result is going to look like a negative number. So if I add two positive numbers and get a negative number, this means I have overflow. Okay. If I add a positive number and negative number, I can get a positive number, that's fine. I won't get overflow from adding positive and negative or from adding negative and positive together. But if I add two negative numbers and get a positive number, well, that's also not possible. And that's also an indication that I have overflow. So in general, if I'm adding two positive numbers giving me a negative number or two negative numbers giving me a positive number, those are indications that I have overflow. If I'm doing subtraction, and it goes without saying that subtraction also means, set on less than, because set on less than uses subtraction. So if I'm doing subtraction or set on less than, if I subtract a positive number and a positive number from a positive number and get a positive number, that's fine. If I subtract a positive number from a positive number and get a negative number, that's also fine. But if I subtract a negative number, that's also fine. So negative number from positive number is fine. But if I subtract a negative number from a positive number and get a negative number, then there's something wrong, right? Because I can't do, if I subtract a negative number from a positive number, it's like adding two positive numbers. So I should not be able to get a negative number here. Similarly, if I subtract a positive number from a negative number and get a positive number, that also is indication of overflow, because negative something minus something positive is not going to be positive. It's always going to be negative. So the cases where I have overflow are these four cases here: adding two positives to get a negative, adding two negatives to get a positive, or subtracting a negative from a positive and getting a negative, or subtracting a positive from a negative and getting a positive. Okay, so these are the cases where we have overflow. Is this clear? Is it clear why in these cases this is an indication that overflow occurred in my ALU? Okay, great. So what I would like to do is I would like to detect if I have any of these four cases. Now, to make things a little easier, what I'm going to do is, rather than looking at B and A, I'm going to look at A and B after the inverters, right? Because we said that subtraction is going to be A plus not B, right? So I'm going to look at A prime and B prime, where they're A prime and B prime are A and B after the multiplexer. Okay, so in this case, for addition, B and B prime are going to be the same. Okay, but for subtraction, B and B prime are going to be opposites. So here, for subtraction, B prime is going to be the opposite of B. So B prime, again, it's B after the multiplexer. So if I'm doing subtraction, B prime is going to be not B, and it's going to look like this. So now if I look at B prime, if I look at not B for subtraction, you'll notice that we have the exact same conditions for add and subtract, right? Because here you'll notice that if I'm doing, if B prime is positive, then I have a positive plus a positive is a negative, that's overflow. And if B prime is negative here and A prime is negative, and I have negative plus negative, that's positive. So that's an indication that I have overflow. So you'll notice that the conditions for subtract and set on less than and for add are the same if I look at B prime. In other words, if I look at B after after the multiplexer. So here I actually don't need to have all these conditions to design my overflow circuit. If I look at B prime, I only need to be concerned with A prime and B prime, because then I'm always going to be doing addition. Okay, so if I look at A prime, B prime, and sum, then the cases where I'm going to have overflow is if I add two positive numbers and get a negative number, or if I add two negative numbers and get a positive number. Okay, now how do I know if A prime is positive or negative? So how do I know? So A prime here, again, this is an n-bit input to my ALU after the multiplexer for A. So how do I know if my n-bit value is a positive number or a negative number? We've seen this before. It's a property of 2's complement. Right, so what does 2's complement tell us about positive and negative numbers? So A is a negative number. A is a positive number if the most significant bit of A is 0. And A is a negative number if the most significant bit of A is 1. Okay, we've seen this before. So I know, so A prime and B prime and the sum, all three of these, where we know they're positive if the most significant bit is 0, and we know that they're negative if the most significant bit is 1. So here I'm gonna, in this pseudo truth table over here, I'm gonna replace these with 1s and 0s. So if my most significant bit here, A prime of n minus 1, this is the most significant bit of A prime. B prime of n minus 1, this is the most significant bit of B prime. So here, I know that A is positive if the most significant bit of A is 0. I know that B is negative if the most significant bit of B is 0. I know that the sum is positive. I know that B is positive if the most significant bit is 0. I know that sum is negative if the most significant bit is 1. So here, if my most significant bits for A and B are 0, meaning they're both positive, and my most significant bit for the sum is 1, meaning it's negative, this is an indication that I have overflow. And similarly, if my most significant bits of the two inputs are 1, which means they are negative, but the most significant bit of the output, the sum, is 0, which means the sum is positive, this is an indication that I have overflow. Okay? Is this clear so far? Any questions? So someone's asking if we can have overflow without affecting the result. So obviously, if you have overflow, that means you've affected the result, right? Because if I add two positive numbers and I have overflow, I'm going to get a negative number, right? So the result is obviously incorrect because you have overflow. How do we detect overflow? That's exactly what we're talking about right now. We're talking about how to detect overflow. So you're asking if we can have overflow without the sign being affected. No, that doesn't really occur. You know, if you add two positive numbers, you can't overflow and still get a positive number because what that means, you have to overflow through all the negative numbers back up to the positive domain, and you can't actually have. You know, if you add the largest possible two positive numbers together, you're gonna get a negative number. You're not gonna go overflow all the way back up to the positive range. Okay, good question. Okay, so now that I have this truth table that tells me when I have overflow, what I can do is I can build a circuit that detects overflow. So here the logic equation. What's the logic equation going to be for detecting overflow? Well, it's going to be the min terms for these two rows, right? So overflow is going to be equal to not A prime and not B prime and sum. Of course, all of them are subscript n minus 1. Or A prime and B prime and not sum. Okay, again, all of them are subscript n minus 1. Okay, so here, this is a logic equation to detect overflow. And what we can do is we can create a circuit that implements this logic equation to detect overflow in our ALU. Okay. Now, what's the how many gate inputs am I using here? What is the cost of this circuit? Yeah, what is my hardware cost here? I have a 3-input AND gate and a 3-input AND gate. That's 6 inputs. I have a 2-input OR gate. That's 8. And then I have 3 inverters. So that's 9, 10, 11. Okay, so I have 11 gate inputs in total. Okay, can we do better than this? The question is, can we have a simpler circuit for detecting overflow? And the answer is yes, we can actually do a better job than this. We can come up with a simpler circuit. And the trick is, no, not using a Carnot map. This is the simplest equation that you will get from a Carnot map. But the trick is that although intuitively it makes more sense to think of overflow in terms of the signs of the inputs and the signs of the output, it turns out that we can do a better job if we express the overflow in terms of the carry-ins and the carry-outs. So let me show you why. So here, if you recall, this is the truth table for the 1-bit adder. Okay, this is the truth table for the 1-bit adder. And these rows in blue over here correspond to the rows in blue here. The rows in yellow correspond to the rows in yellow. And then the rows in orange and green correspond to the rows in orange and green. So what do you notice here? Well, we'll notice, so overflow here corresponds to the rows in orange and green. And we don't have overflow for the blue and yellow rows, okay? So let's go over here in truth table and take a look. So you'll notice that for these blue rows, carry in and carry out are 0, 0. Okay, here there's 0, 0, here there's 0, 0. For the yellow rows, carry in and carry out are 1, 1. So here we have 1, 1, 1, 1, and 1, 1. Okay, and then for the orange and the green rows, carry in and carry out are 1, 0, and 0, 1. Okay, so what we can actually do is if we express our overflow in terms of carry in and carry out, as opposed to expressing it in terms of A, B, and sum, we can get a simpler equation. And let's take a look at that. So from this truth table, we see that our overflow is 0 whenever carry in and carry out are 0. This corresponds to the blue rows here and the blue rows here. Our overflow is also 0 if for the yellow rows, these 3 yellow rows can all be summarized with carry in, carry out being 1. And then what remains is the cases where the carry in and the carry out are different. So if carry in is 0, carry out is 1, or carry in is 1 and carry out is 0. These are the cases where I have overflow. Okay, so it's less intuitive to express overflow in terms of carry in and carry out. But if we do that, we can actually get a more efficient circuit. Okay, so let's take a look at this. How do we implement this equation over here? Well, it's simply not C in and C out, or C in and not C out. Okay, so your overflow is equal to C in n minus 1 and not C out n minus 1, or C in not C in n minus 1 and C out n minus 1. Okay? What's the cost of my hardware here? 8, exactly. We have 2 ANDs and 2 ANDs, that's 4, and then a 2-input OR gate, that's 6, and then 2 inverters, that's 8. Okay, so we have 8 gate inputs. So by expressing overflow in terms of C in and C out, even though it's less intuitive, it actually gives us better performance. And there is an intuition here, by the way. There is a reason. There's kind of a logical reason why this happens. You know, if my carry in is 0, but then my carry out is 1, it means I have 2 1s in my as my most significant bits. But if I carry those out, that means the remaining value is going to be a 0. So here I had 2 1s become a 0, and that's kind of what's going on over here. Okay, any questions about overflow? Okay, well, to support overflow, what we're going to do is we're going to, in our 1-bit ALU, remember we said we're going to have a different 1-bit ALU for most significant bit. In our 1-bit ALU for the most significant bit, we're going to add an overflow detection unit over here that's going to take, various inputs, and if it detects an overflow, it's going to output a flag that says that there is overflow. Okay? So this is what overflow detection is going to do. And then finally, this is going to be passed as the output of our ALU. So now our kind of n-bit ALU has multiple important outputs. We have the result, which is an n-bit value, but then we also have the 0 flag and we have the overflow flag. These are going to be the outputs of our ALU. Okay? All right, finally, let's move on to kind of our final topic. So now that we've designed an n-bit ALU from this 1-bit ALU, the question is, what am I going to set my control lines to perform each of the operations? So if I want my ALU to perform an AND, my operation is going to be the combination of A invert, B invert, and select, okay? So if I want my ALU to perform an AND operation, what will I select my control lines to? If I'm doing an AND operation, what's select going to be? No, I'm doing an AND operation, so here select is going to be 0, 0, right? And what are A invert and B invert going to be? Right, A invert is going to be 0, B invert is going to be 0. So if I pass 0, 0, and then select is going to be 0, 0, if I pass this to my ALU, that's going to perform an AND operation. As for C and 0, I don't care about its value, right? I don't care about C and 0 because that's only going to go into the adder, which doesn't affect the AND operation. Okay, so 0 for A invert, 0 for B invert, don't care for C and 0, and 0, 0 for select. This control signal will make the ALU perform an AND operation. What if I wanted to perform an OR operation? What am I going to do? What's A invert going to be for OR? 0. What's B invert going to be? 0. And what's the select going to be? 0, 1. Exactly. So my control signal for the OR operation is going to be 0, 0, don't care for scene 0, and 0, 1. Okay, so a 0, 1 will select this OR gate, and I don't want to invert the input, so I'm going to put 0 here to pass A to the OR gate. I'm going to put 0 here to pass B to the OR gate, and then I'm going to select the result of the OR gate. Okay, what about NAND? What about NAND? What's my select signal going to be if I want to do a NAND operation? Right, exactly. So remember, a NAND is an OR gate with inverted inputs. So a NAND will be an OR gate with inverted inputs. So I want to select the OR gate 0, 1, but I want to invert the inputs. So I will set A invert and B invert to 1, 1. Okay. What about NOR? And of course, I still don't care about C and 0 for NAND. What about NOR? Right, exactly. So for NOR, a NOR gate is an AND gate with inverted inputs. So I'm going to select the AND gate here, but then I'm going to invert the inputs. I'm going to select 1 and 1, and C and 0 is going to be 0. So this is NAND and this is NOR. 1, 1, 0, 1 gives me NAND, and 1, 1, 0, 0 gives me a NOR operation. What about addition? What control signal represents addition? Okay, so I'm going to have A invert is 0, B invert is 0. This will pass A and B to the adder. And then I want to select the result of the adder, so that's going to be 1, 0. So I'm going to do 0, 0, 0 here, 0 here, 1, 0 here. I still have C and 0. What's C and 0 going to be? It's not going to be a don't care this time because I care about the value for addition, right? It's going to be 0, exactly. So I'm going to have 0, 0, 0, 1, 0. This gives me addition. What about subtraction? Right, so for subtraction, I'm still going to use the adder, but the difference is that I want to invert B, right? So I'm going to have a 0 for A invert, a 1 for B invert, and then I'm going to select the result of the adder, so I'm going to have a 1, 0 for select. What about C and 0 for subtraction? Right, C and 0 is going to be 1 for subtraction. So remember, for subtraction, we need to add the 2's complement. So we invert B and we also add 1 to C and 0. So for subtraction, we're going to have 0, 1, 1, 1, 0. Okay, this is going to be the result for subtraction. What about set on less than? What are going to be my control signals for set on less than? So remember, set on less than uses subtraction, right? Set on less than uses subtraction. So I'm going to have the same inputs for subtraction. So these are I'm going to invert the second input and have C and 0 be 1. So I'm going to have 0, 1, 1. But I'm not going to select the result of the subtraction. I'm going to select the result of less. Okay, so we're going to have 0, 1, 1, which is the same as subtraction, but then for select, we're going to select this last value over here, which is 1, 1. So here in this table, what we have is we have the control signals for each of the operations that we want to perform. So here what we can do is we can control what operation the ALU does by passing the right control signals. So someone's asking, for 2's complement, don't we need to subtract 2 to the n for the result? So right, when we get so 2 to the n is going to be the overflow bit, right? When we add two n bit numbers, right? The 2 to the n that we get is the last bit, and that's going to be 1, and we simply ignore that, right? So if we add two negative numbers or a positive number and negative number, we get an overflow bit. That overflow bit, by simply ignoring that, that's equivalent to subtracting 2 to the power n. Okay. All right. What do you notice about C in 0 and B invert? Is there anything interesting in the relationship between these two? Right, they're equal, exactly. So here, when you know, some places we don't care about C in 0, and then in some places where we do care about C in 0, it's always equal to B invert. Why? The reason is that when are we inverting B? Well, we're inverting B when we're subtracting. And when are we setting C in 0 to 1? Well, we're setting C in 0 to 1 also when we're subtracting. So you'll notice that C in 0 and is equivalent to B invert. So it's actually redundant to have both C in 0 and B invert. We can simply connect C in 0 and B invert to the same wire. And that's actually what happens. So here, if we look at our n-bit ALU, our operation is going to be composed of 4 bits, 1 bit for A invert, 1 bit for B invert, and 2 bits for select. And C in 0, for C in 0, we're just going to connect B invert to C in 0. Okay? So finally, this is our n-bit ALU that we've built. It takes an n-bit operand A, an n-bit operand B, gives us an n-bit result. It also gives us a flag that tells us whether or not the result is 0. It gives us a flag that tells us whether or not we have overflow. And it also takes an operation signal, and the result of the operation signal, or the control bits, are going to be these bits over here, depending on what operation we would like to perform. And with that, we are done designing an n-bit ALU. From now on in the course, when we draw this symbol over here to indicate that we have an ALU, now you know how this is implemented. Any questions about n-bit ALUs? All right, if there are no questions, then that is all for today. You can refer to section B.5 or the rest of section B.5 for if you want to read more about the material we covered today. That is all for today, and I will see you next time. Next time, we'll start talking about sequential logic. Bye, everyone.